Okay, good day, everyone. Thank you for joining us for this webinar presentation. My name is John Clements with the Homeland Defense and Security Information Analysis Center and the Defense Systems Information Analysis Center, which are two of the IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, or DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. HDIAC supports those working in the Homeland Defense and Security domains of DoD research and engineering. We do this by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. We provide research and analysis services to help unlock access to information, knowledge, and best practices from the government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We provide a technical inquiry service in which government researchers, including contractors, can receive 4 free hours of technical research. To learn more, go to hdiac.org or dsiac.org and click on the Technical Inquiries icon. We hope you enjoy this webinar and that it serves as a catalyst for community collaboration and improved DoD Homeland Defense and Defense Systems research. Before we begin, I'll note a couple of administrative items. First, if you're dialed in by phone and would like a copy of the slides, they were posted to the HDIAC webinar announcement. You can go to hdiac.org/webinars and find today's webinar. When you click on it, at the bottom of the announcement, it'll say View Webinar Slides here, and you'll be able to download them there. Second, all participants are muted, but you can chat with the presenters and moderators using the chat box to the left. However, if you would like to pose a question for the Q&A session at the end, please use the audience question tool at the top center of your screen. It is the icon that looks like a chat bubble with a question mark right next to the emoji. At the end of the presentation, I'll go over the Q&A, and for the benefit of those on the phone, I will read the questions out loud to the presenter. If you have a technical issue during the presentation, have no fear. The full presentation will be available online. Check back to the HDIAC website, and once the webinar is posted, the Go to Webinar button will take you to the YouTube link. And with that, I would like to introduce today's presenter, Dr. Frieden Shubididze. Is an associate professor of engineering at Dartmouth College. His research programs are focused on the development of advanced electromagnetic sensing technologies for hardware and software for the detection, location, and identification of subsurface unexploded ordnance, landmines, improvised explosive devices, underground utilities such as wires, pipes, and tunnels. Additional interests include computational electromagnetics, genome sequencing, magnetic nanoparticles, and bacteriophages for cancer treatment. Professor Shubididze is a senior member of the Institute of Electrical and Electronics Engineers, or IEEE, and earned his MS in 1994 in radio physics and his PhD in 1997 in physical and mathematical sciences from the Tbilisi State University in Georgia. He is senior engineering physicist at the White River Technology Incorporated in Lebanon, New Hampshire. Professor Shubididze is the DoD's Strategic Environmental Research and Development Program 2011 Munitions Response Project of the Year Award for the development of advanced EMI inversion models and UXO classification strategies. He is a native of the Republic of Georgia and was awarded the Georgian Medal of Honor by the country's president in 2019 for his personal contribution in the development of science and the creation of modern technologies. Dr. Shubididze, please take it away, and the floor is yours.
Thank you for introduction, and please welcome everyone on this talk. Today I will talk on advanced electromagnetic induction systems for subsurface target detection and identification. And before going and diving into the presentation, let me point out that this is a close collaboration work between Thayer School of Engineering that I am presenting here and Cold Regions Research and Engineering Laboratory, which is U.S. Army lab here in Hanover. And my colleague Ben Barrows, Dr. Ben Barrows, is on on webinar here. And if you will have some questions, he may answer some of questions related to his work here. So we have here a formal group. We call this electromagnetic sensing groups. We have extensive experience in detecting and classifying buried explosive hazards. We started this just solving fundamental low frequency electromagnetic induction problems. Then based on the physics, we come up with a new development and design advanced EMI system as well as a data processing algorithm, which then was tested and validated on various live UXO sites, as well as for ID heat detection and classification systems. Currently, we are building and testing lightweight subsurface sensing technologies. And namely, we are building handheld devices as well as a system that will be mounted on UAS platforms. So when we talk about buried explosive hazards detection and classification, as a first step, we take a range of targets and divide them into three main categories. First are metallic targets, where we have projectiles, mortars, rockets, different size, shapes, and what they have common that all of them are made with metals, or they have substantial amount of metals. And then recent development in material science, nowadays we have also intermediate conducting materials that are used as a explosive devices, such as carbon rods, depleted uranium, and this type of material has less conductivity, electrical conductivity than metallic targets. And then this type of targets we call intermediate conducting materials. And then third one is a non-metallic targets. Those are plastic mines, homemade explosives, and other type of materials. So each of this category will require this. We'll go down and show some of the results. Will require different frequency range or different type of sensing technology in order to detect and identify this type of materials and targets. Now, let me start with describing unexploded ordnance problems, which are, as I said, mostly are made with metals or containing substantial amount of metals. Those problems comes from First and Second World Wars. As we know, many European countries have these unexploded ordnances. Just last century, Southeast Asian countries during Vietnam War, there were lots of bombs. By approximate, there was 270 million bombs were dropped, and out of 270 millions, 80 millions are estimated they did not go as extended, and they failed to explode. And then now still remains a problem for those countries. We have active and former military bases, which are very high contaminated with these unexploded ordnances. And then recent days, we have these cluster bombs, which makes threat for public for a long time. Now, if you look United States, countries that never had this major big wars here, UXO problem here are quite significant, and it was identified as an Army's #1 environmental problem back in late 90s. And it's because that approximately 11 million acres of land are impacted with UXOs. And if you take in prospect, this is roughly area of New Hampshire and Vermont combined. And in addition that there is a documented that around 10 million underwater areas are also contaminated with this unexploded ordinances. So when we talk about surface target detection, immediately we look the sensing or detection technologies. Nowadays we have magnetometers, which and the electromagnetic induction systems, and those systems detect metals and are widely used for detecting targets. Then we have ground penetrating radar, which operates at high frequencies, and this system detects metals as well as the dielectrics. Ground penetrating radars are not in service everyday use for detecting these explosive hazards, and mainly this due to the false alarm rate. And then we have animals that we used for detecting these explosive hazards. And then we have nuclear detection systems that still are in labs or being developed as we are talking. So now, because UXOs contain substantial amount of metals, they can be easily detected. But the problem is the identification. And practice, we have seen that for finding one UXOs, there is more than thousands of false positives. So in perspective, what happens that cleanup cost goes to tens of billions of dollars, and then to reduce this cost and expedite UXO cleanup process, classification is a solution, and that was the main focus of our group in last 20 or so years. So now, when we say classification, you can look the problem and divide into three main categories. First is we need a sensors that will provide data, high fidelity data. Then we need signal processing. We call this data inversion. We take data, apply physics-based models, and extract some targets feature parameters. And then last step is to use these feature parameters and classify or called identify UXOs among exploded targets or among clutter. So that's a main steps we have taken to achieve classification goals here. So now for this problem, we are using electromagnetic induction sensing. And electromagnetic induction sensing, in few words, you can imagine as follows. We have a sensor which produces this transmitted magnetic field, or we call this primary magnetic field. It is at the low frequency. We are talking about 10 hertz up to 10 kilohertz, very low frequency. And this electromagnetic field penetrates inside the target and induces eddy currents or magnetic dipoles. So those eddy currents then produces secondary field, which are detected with receivers. And we use this detected signals to extract the target's feature parameters and use those parameters to make final decision about targets, to classify them. So if you look this in a time domain sensing, you can look as in transmitter, we have current that's we turn on this current achieves or gets to the constant value after a certain time. We hold this constant current, that means magnetic field around targets. This magnetic field penetrates inside object, and then we turn off. And when we turn off, based on Lenz's law, this this currents that are inside of this object will inside object will be induced currents that will oppose this change of the magnetic field. And then once we have taken out our primary field, we have set of receivers and our receivers will sense a magnetic field coming from the target itself. In comparison between frequency domain and time domain sensing technologies, one of the nice thing for time domain system is that we can put as many receivers as we want, whereas in case of the frequency domain, which is a continuous wave, we have to back up primary field, and that's it. In scientifically, it is easy problem for one or two receivers, but to get this in field and to in actual practice, it's quite difficult and challenging problem. So based on this understanding, as I said, we studied this from basic physics, from equations and developed technologies. Our group have recently built this ultra-lightweight electromagnetic induction arrays. One is a handheld device, what you have seen, we call this ULEMA, and then similar technologies. Because of this lightweight, we managed to adapt on UAS system, and we are able to collect some data and process and do classification. So now, it's a brief description of the first part. When we have sensors, we collect data, and once we receive data, those data we can build a detection map. And here is some representative of detection map using these EMI systems. And every hotspot there, these red dots are potential target. So as I said, as the next step here, we have to take this data and apply algorithms, process this data and extract target feature parameters to make a classification or to identify which are clutters and which are unexploded ordinances. This will require to have again very robust models that will captures all characteristic of the object and then will extract targets parameters from data. And just for illustration, one of the kind of simplest model that's widely are used is a dipole model. The idea here is that we can take a target and then target can be replaced with a magnetic dipole, one or set of magnetic dipoles. And each dipole, then magnetic dipole, produces secondary field, and then strength of this magnetic dipole is scaled respect to the primary field. The normalized or unscaled magnetic dipole moment or polarization along target's main axis are property of this object, and they are independent on the object orientation, location, respect to the sensors. And those polarizabilities, that's what we will be as we will, I will progress, I will show those are property, and we use them for classifying targets here. So this technology was developed in the last more than 20 years, and was tested on actual live UXO sites. Projects were developed under CERDEP ESTCP, and CERDEP spells for Strategic Environmental Research and Development Program, and ESTCP is a environmental security technology certified program. And they did live UXO studies, and one of the first site was Camp Butner in North Carolina. Here is a aerial view. They choose an area which was mixed of native clutters and mostly native UXOs. And then they also inserted or buried some tested targets in order to get a statistic of potential UXOs. And approximately they choose 2,500 anomalies for intrusive investigation, meaning that once targets were detected without processing this data, they dug these targets and documented which was UXOs or unexploded ordinances and which were clutters. And none of the information were given as for to assess our algorithms. So we got these data sets and we went and processed this and extracted, we call this magnetic polarization, which is effective magnetic dipole along target's main axis. We extracted those polarizabilities. It has three polarizabilities. One is along target, which slowly decays, and there is a two polarizabilities orthogonal to the main axis. And for the symmetric object like a UXOs, those two we call secondary or tertiary polarizabilities, they are symmetric, then their values are same. Here I am showing extracted polarizabilities from actual data sets. And then these targets were buried at, as I said, at different location and orientation with respect to sensor. And what main take home information here is that this extracted polarizabilities is a characteristic of the object. As you see for UXO targets, they are very well clustered and shows symmetry. Whereas if we take a horseshoe here, we can see that those polarizabilities are at least two of them are not coincide to each other and they have different properties. So we use this extracted polarizabilities then to make a classification. And here is a independent scored classification results for Camp Butner in terms of the ROC receiver operating characteristic curves. So the red one is that when we said this is a UXO and it turns out it was correctly identified, that's we go up. And then on x-axis from green lines are targets that we said those were not UXO, we say the clutter, and it turns out to be correct. The blue dot is where we say to stop dig, and then it turns out that at that point we were able to classify our TOIs. There was around 100, there was 171 targets, and we classifying them, all of them, as a UXOs, as well as we classify them by types, meaning that we are able to distinguish 37 millimeter from 105 millimeters, as well as a small nose piece of the UXOs that we are identified also as the targets of interest. So this system and signal processing approach were taken and tested more than 20 live UXO sites, and here are some representative of those sites, and extensively studied classification performance. And here are some of them where we had sites that was in wooded area, as well as in very challenging areas as a Fort Ord, which is a very cluttered UXO sites. And then by doing this signal processing approach, our technology was able to identify them accurately and almost in all UXO sites. So just recently, we also did studies for underwater. The system was taken and collected data on underwater UXO sites. That this is a just test site, and I am showing here a calibration detection and extracting this polarizability is for some of the UXOs. So basically, would say that the technology that was developed for land-based now it is applicable for underwater UXO problem as well. There are, of course, underwater lots of engineering challenge, but the main information I want to convey is that the sensing technology can be used for underwater UXO detection and classification. After all, engineering problem for underwater environment will be resolved or will be mitigated. Here is another results also, like our systems was adapted on UAS system. Was data was collected last year, and here are some extracted these polarizabilities for targets. In this case, for 105. 155 millimeter projectile, and this technology is able to detect and identify this target. So from the beginning, I said that there are metallic targets that are hazardous, as well as nowadays we have this intermediate conducting low targets, which has low conductivity. So if we deploy here this metal detectors, the question then comes: will they work? Will they sense and detect these intermediate conducting targets? And can we use this technology directly applied to for detection and classification intermediate conducting targets? To answer this question, we did some modeling studies before building a system, and it turned out that indeed this existing technology are not suitable for detecting and most importantly for classifying these intermediate targets. So if you look at signal from the metallic targets, electromagnetic induction signals, it has two parts. One is a in-phase part, and we have quadrature part. This quadrature part has a peaks, and those quadrature part is a information or relaxation that is characteristic of this object. And in order to classify, we need full information of this relaxation. And then modeling shows that if we use a standard frequencies, which goes up to 10 kilohertz, and for same size target with less conductivity, small conductivity, we can see that it's we are not capturing entire this relaxation, meaning that maybe we will be able to detect, but will be very difficult to classify. So these results led us to come up to conclusions that in order to detect and classify these low conducting materials, we had to push a frequency for the standard electromagnetic induction sensors towards to high frequency. And that's to achieve this, we build a high frequency electromagnetic induction systems system. Originally, it was built for environmental research and development centers, U.S. Army's ERDEC centers, in collaboration with CREL. And then this technology here for the next level of testing and improvement was also funded by the ONR. It's still ongoing project. And here I am showing the comparison for detecting these ID targets, which has this low conducting material such as carbon rods built as a pressure plate, and we are showing using high frequency HF EMI and standard metal detectors. And from the results, you can see that this high frequency EMI system is able to detect these low conducting materials. And here is a detection map for, again, carbon rod using standard metal detectors. Its view barely shows the response, which can be used for detecting shallow targets, but for a deeply buried target, it was very difficult to detect. Whereas high frequency EMI system, which shows full spectrum for buried targets, it detects as well as this relaxation will provide us information to classify, not only detect, to classify. So recent development is that we are taking this system and making more robust, faster to collect data, and then finally build and deliver this handheld device that will operate from 100 kilohertz, maybe up to 20 megahertz. So next system that's our group working is to develop a system for infrastructure detection and mapping. In the United States, there is more than 35 million miles of underground utilities. That's over time they start, particular pipes get corroded, and there are need now to detect them and assess their conditions. Again, the sensing technologies that exist are magnetometers, traditional EMI, ground penetrating radars, as well as the acoustic sensors. And then in order to detect these targets underground infrastructures, and particularly um, targets that has a very low amount of metal, such as tracing wires, are very difficult with this traditional sensing technologies. And our group, based on our experience on high frequency EMI, we are pursuing to develop this linear current sensing technology. And we have built this prototype system, which is based on gradiometers. It measures vector magnetic field, and difference between traditional and then linear current sensing technology is that in the linear current sensing technology, we use the electric field as a excitation and then receive magnetic field. Whereas for the traditional EMI sensing, we use magnetic field for excitation as the primary field, as well as as well as magnetic field for receiving here. And here are some detection maps. When data were collected here locally, we lay down different size wires, different length wires, and different gauges as well. And those traces, you can see those are detections when we are passing about wires, and depending on length and the location of the sensors with respect to respect to the receiver systems, we are able to detect these wires using this system. As well as that, this system was tested for subsurface wires detection. And here we have a case when wires were two parallel wires were buried at different depths, and uh, we not only detect, but we are able now to process this data and pinpoint the depths of this wire, as well as their X and Y location on GPS coordinate system. And as I said, it works for not only single buried wires, but also for more than one wire, for multi wires as well. And then finally, just to give you one more sensing technology that we are developing is we are developing EMI system, putting on drones for mapping to map permafrost in Alaska. The idea here is that the sensor will fly at different elevations, and we will be collecting vector data sets. Vector data sets, and then using these data sets, extract soils electromagnetic parameters and pinpoint out location of permafrost, which is a big problem in Alaska. So with that, I will stop here and we'll take questions you may have. Thank you.
Thank you very much for the presentation. I do have one question, at least so far in the queue, and I apologize if this was answered throughout the presentation, but I just wanted to know myself, what depths can this technology work in? I guess I mean in different terrains. What are the depths that this works to?
So if we are talking about in the electromagnetic induction sensors for unexploded ordnance detection and classification, it is proved that existing technology can detect and classify targets up to 11 times target's diameter. So that means that if we have, for example, 37 millimeter projectile, we can detect and classify it up to 40 centimeter.
Wow.
So if we have 105, it comes around 4 feet.
Outstanding. So I'm going to go ahead and just pause for a moment and see if any other questions coming from the audience. And I will say to please submit them using the Q&A function at the top center of your screen. It should be right next to the emoji. And if you want more information on this topic, you can please reach out to myself to get in touch with Dr. Shubadidze. You can email our contact alias, which is contact at HDIAC.org or contact at DSIAC at .org to reach and get more information or submit a technical inquiry to us. So, sir, at the moment, I don't see any other questions. I did get one more. Here we go. Just the last second, just got in. I'm wondering if using a pulse or pulse shape versus a continuous frequency would help. From Eric Timpson. Is that something that you guys have explored at all?
So for UXO technology, that's a good question. Actually, yes, we use pulse. Basically, we are pulsing currents. We turn on current and holding up to 10 or 20 milliseconds. Then we turn off, collect data 10 or 15, 10 or 20 milliseconds, and then we turn on, turn off. So we are pulsing this system. Yes, that's It works very well for low frequency. For high frequency EMI, when comes down to have this faster switching back and forth, we have challenge. We are considering and looking way to manage and develop or build a system that will be pulsing. But at this moment, we use continuous wave for high frequency.
All right, great. Well, at this time, there's no more questions. So, Dr. Shubidise, I thank you very much for the informative presentation. For everybody else on the line, if you wanted to share this presentation or if you know somebody who couldn't be here, it will be posted up on YouTube after about 24 to 48 hours. We get it up on the HDIAC YouTube channel. So please stay tuned for that. And with that, thank you very much, sir, for the presentation.
Thank you. I think there was one more question.
Oh, I see it went into the chat. Brian Wilmer, could you talk about battlefields littered with fragments and other metal items?
So, well, that's a very contaminated. For UXO problem, we have not done any actual testing in battlefield. So UXO is more safe, so we can go back and collect data. But for HFEMI, handheld device for ID detection, we are considering this once it will be mature enough to go and test more robustly. That's what we are targeting. Our experience and understanding is that the frequency range we are considering should allow us to distinguish, for example, ID, which will have wires, maybe pressure plates made out of the low conducting materials. They have very distinguishable features compared to metallic fragments, and that could help us for classification, identification of this dangerous targets. But we have not done this actual testing in field at this moment. Should be next step.
Very good. One more time, I will pause briefly to see if any more questions pop in. Keep my eye on both the Q&A and the chat. All right, sir, one more time, I'll try to close it out and say thank you so much for the time and for presenting this information, and continued success. Very much appreciate your time today. Thank you.
Thank you.